Cool. Hey everyone, my name is Brian. I'm a senior AI engineer at LinkedIn focusing on responsible AI. Today, I'll be giving a talk on one of our papers, Disentangling and Operationalizing AI Fairness at LinkedIn. And to preface the topic, a lot of papers focus on the study of like algorithmic bias and fairness right now, especially in the computer science domain. What I want to do is take a step back and think about how we actually put these papers into practice in terms of, when do we find it reasonable to use a certain algorithm or another? How do we think about the things that algorithms cannot correct? So this is really taking a step back and considering the bigger question of how do we operationalize all of the developments that have come out of the academic world in fairness. So getting started, this is the agenda for today. So I'll first start off by discussing a bit about what fairness means in the context of LinkedIn. And I'll entangle these two topics, equal treatment and equal opportunity, as we're calling them. And I'll talk about that through the lens of our three principles approach, which you see here, including a short interlude on a different paper about algorithmic bias that does tie into the broader topic. And I'll talk about a case study where we actually discuss applying one of these algorithmic fairness principles or algorithms on a real LinkedIn product and ramping a model and give some directions on our current research right now. Cool. So starting off, what does fairness mean at LinkedIn? So searching for a candidate, if you're a recruiter and you find 100 candidates and you see that 80 are male and 20 are female, one can ask the question, is this unfair because we didn't get a 50-50 distribution? Well, from one perspective that I'm going to call equal treatment, perhaps one would say not really. If the model is predicting correctly for real-world qualifications as accurately for one group as another, then it's fair. And so this is commonly referred to in literature as predictive parity. But from another perspective, you may say this is unfair because there may have been historical barriers that have prevented females from obtaining the same qualifications in order to show up at a 50-50 rate. And so this is commonly called demographic parity. So there's these two conflicting kind of objectives, and anyone who's read a little bit about fairness, I think will come across this notion very quickly that fairness has these different definitions and they're mutually incompatible a lot of times. So here's 21 fairness definitions, and I couldn't find the original source of this diagram, but we found it to be very helpful in illustrating the two problems of equal treatment and equitable outcomes. It's not really possible to satisfy both, even though depending on your worldview, both are good things to have, or could be good things to have. So the real question is, how do we, as an organization, working with AI in our models, AI is integrated into basically every single LinkedIn product. How do we disentangle these two things, right? So we consider AI fairness to be a sum of equal treatment and product equity. So what do I mean by that? First of all, from an equal treatment standpoint, we basically want to make sure that AI systems can guarantee this. So this is to say that we want our models to really be predicting real world qualifications. And we see this as like a necessary but insufficient thing. So that's to say that, maybe our models predict equally, but we know that that's in the long run potentially not enough. And that's why we have this other notion of equitable outcomes. So this is to say that equitable outcomes have to be driven by product strategy. These are things that algorithms cannot necessarily fix. These are things like historical barriers. These are things like societal biases. And fixing these things can take various different forms, and I can give a couple examples later. And you can see from a algorithmic bias standpoint, these two definitions are in stark contrast with each other in terms of how we measure things, in terms of the objectives that we're going after. So instead of basically forcing both of these definitions onto the algorithm and trying to find a balance, we actually say from an algorithmic standpoint, we go after predictive parity, and from a product standpoint, we go after demographic parity. So that's the idea here. And hopefully in the long run, maybe one goes down and the other goes up, but in net total, they're both going up is what we would hope to see through this framework. Okay, so the three principles lens that I was discussing earlier was basically this idea that one will look at algorithmic bias through this equal treatment lens. And so we'll work to measure and mitigate algorithmic bias so that our AI systems treat everyone equally. As an AI engineer, this is exactly what I work on. I work on developing methods and for measuring bias, as well as methods for mitigating bias in our models once we do observe them. The second lens is pursuing equitable outcomes through a product standpoint. So this is to say we don't consider AI treatment the end of our work, but we treat it more as a foundation of a broader fairness strategy that LinkedIn hopes to pursue. And the last is that we hope to validate our approach by broadcasting this information externally and trying to lead with transparency in this field. I think a lot of times it's very difficult to talk about these things, and like even to push this paper out. We had to like go through a lot of internal discussions with our lawyers and like have them give the go ahead before we do anything. And as a matter of fact, if you look at the paper, the lawyers' names are on the author list. So they can't get mad at me for presenting this. And so like it's difficult, but we feel that it's very important to be transparent with these things and get external validation through, conference presentations, writing papers and blogs. And we'll hope to continue doing that. So now I want to get into the details. And this is what I think is interesting because not too many companies go out and like tell you exactly how they want to operationalize these things or like which algorithms they use or it's for measurement or for mitigation. So I hope to give some color there. First of all, we have to measure algorithmic bias in our models. And to do that, there's different criteria depending on how the model is actually being used. So for example, if we're thinking about generative AI, there we might want to measure stereotyping. For ranking algorithms, we might want to measure allocation harm. And when I say allocation harm, I mean in the sense that in a rank list, the ranks are a scarce resource. So one person getting rank one automatically means another person cannot get rank one. But in other systems like viewer side fairness, where maybe you're ranking products that don't necessarily have direct fairness qualities, think about like jobs, the job recommendation algorithm at LinkedIn, we would use something like a viewer side fairness notion. So measuring things like, are you receiving a proper minimum quality of service? And so through these, for each type of algorithm and their intended use case, we have different ways of measuring fairness as well. So to give you some more detail, principle one, measuring algorithmic bias, we can decompose the situations roughly as follows. If you're viewing things that, again, don't have some notion of scarcity, like if it's a rank list of jobs, if it's ads perhaps, then we care about things like viewer side fairness. So here you see an example where it's like based on your country, are you getting a proper bar of service, or is your AUC relatively low compared to the rest of the population? And then there's other situations where we're actually ranking people or candidates. So then the question is, are we being fair when we compare candidates to each other? So examples here could be things like people you may know, which is our network formation algorithm, or it could be recruiter search, which is what recruiters use to find candidates across LinkedIn. So there, depending on the type of model, we could go after things like predictive parity, which basically checks if the expected outcomes conditioned on the score are equal across different groups. Or we could look at notions of ranking-based fairness, which I think is quite interesting and not as widely discussed, but has a lot of applications because in real situations, the score doesn't matter so much as the rank. And in e-commerce, at LinkedIn, in even some medical contexts, sometimes it's the rank that matters instead of the score. So this is an area that I think isn't as widely discussed, but it's also very important. Okay, so in terms of how we actually use these algorithms, right? What we do is follow essentially a four-step runbook for bias mitigation. So number one, we start by investigating potential root causes of bias. So I'll talk more about details at some point, but essentially what root cause analysis means is trying to identify why bias exists from the lens of the data. So these could be things like distribution shift, if you're familiar with that line of literature, or it could be things like understanding is one population particularly underrepresented in the data is a common thing to look at. So running these basic checks gives us a notion of why these biases can occur. But that's not necessarily the end story, and it doesn't always tell us exactly what kind of mitigation we use. And there's a lot more details behind it, which I'll talk about at the end if we have time. The second thing is once we've done this basic root cause analysis, we want to identify alternative mitigation strategies without using demographic data. Okay, so this sounds simple, but this in some sense is actually the most difficult part. Because when I say alternative mitigation, I mean algorithms that don't directly use bias that don't directly use the group information at inference time. So if you use group information at inference time, in some sense, it's very easy to fix these biases. Like in a lot of cases, all you have to do actually is just like include the group as part of the model, and you won't even identify bias to begin with. And there's even some theoretical literature showing that even if you don't have the groups, if your features are informative enough to identify the groups, your model will already be unbiased. So trying to fix model bias without using the group data at inference time is actually of like very important, very high importance to us, both for legal reasons and for operational reasons. You don't always have the group information, and sometimes even if you do, it's very noisy. And B, from a legal standpoint, this is just like for now in society, not something that everyone like is okay with. And so like we want to build the narrative that if we need to fix algorithmic bias, then we need to basically be very thorough in trying to do everything that doesn't use group information before we get there. So that's why we call it like a justifiability framework. You'll see that term in the paper. It's because if we want to fix algorithmic bias by using group information, we have to justify it. And so that gets to the third step, which is identifying and monitoring unintended consequences if mitigation does use demographic data. And so here, an example of unintended consequences could be something like, imagine in people you may know, we somehow induce an algorithm to increase the ranks of females. And in doing so, are we causing any unintended consequences in the sense of, are they now receiving more spammy invites? Are they now receiving more unwanted connections? So these are things that we would actually check to make sure that our intended fairness doesn't result in unintended downstream effects for the user group. And lastly, we would launch mitigation, and based on the approval of legal on the product team, with our team, we would monitor what happens in terms of the usual product metrics and business metrics. So if this sounds like quite an involved process, it's because it is. And like there really are a lot of communications that go on between our team, the product team, the legal team, to make sure that we do our due diligence, essentially. That's really the key here, doing the due diligence to make sure that whatever methodology we use at the end of the day is actually justified because the other things didn't work, and also because we know that there aren't any unintended consequences. So I'll stop here because for a minute, because this is a big topic, to see if there's any questions. Otherwise, go on. Cool. Okay, so I'll stop here for a brief interlude about what is the right fairness definition to use. And so this is, I think, like highly discussed in a lot of realistic fairness scenarios, and not so much in the academic papers, actually. A lot of papers will like pick one or pick multiple and say like, the choice of the measure you want to use is up to the user. But realistically speaking, like determining which one is actually incredibly hard from an industry or practitioner standpoint. So, one might ask, like, how reasonable are these canonical definitions, like predictive parity, equalized odds, demographic parity? These are the ones you would learn if you're getting into fairness. There's notions of individual fairness, if you've read some of Cynthia Dork's literature. And how do we know what to do if fairness definitions conflict with each other? And from an industry standpoint, what do we do if the fairness definitions conflict with your business metrics? And so sometimes even meta factors can play into this, right? So like, is the metric scalable in an engineering, not mathematical sense? So for example, if you want to use a notion of individual fairness, one way is to define a distance metric, right? Distance metric between individuals. And that's not always possible. Like I can't, as a person in a company, go to every product team and ask them to tell me like, what is a distance metric that makes sense to you? So even though something might be very mathematically elegant, it has to be scalable from an engineering standpoint if you want to broadly apply it to different product types. And how interpretable is the metric to non-technical stakeholders is actually also very important. So again, like some of these notions I think are quite interpretable. Like I think demographic parity is the most natural notion that people have, both in and outside of algorithmic fairness. So this comes very naturally, and a lot of people like it for that reason. Even though it might not always be the right thing you want to do, it's what's easy to think about. So, in order to deal with this problem, one thing that I worked on was this paper here called Pushing the Limits of Fairness and Possibility. And this basically, I'll go on a side tangent for a few minutes, just because I think this does play into the larger message. The key question is that, like, if you know that these fairness metrics conflict with each other and they conflict with the original model objective, what are you to do about that? And can you do something that optimizes or like tries to give you a sense of what you can possibly achieve? So the way that we approached it was essentially with optimization. So if you write out the problem of trying to essentially maximize the closeness of your scores to your original scores in a post-processing framework. So you have a model that produces scores, and now I want to essentially rearrange scores across bins in order to maximize fairness in some sense, as well as like maintain where the scores originally are. So it's a trade-off between like changing your model scores and achieving fairness by changing them. And as it turns out, you can actually write these canonical fairness definitions, the demographic parity, equalized odds, predictive parity, as optimization constraints. There are some nonlinearities and non-convexities, but it turns out through some optimization trickery and some integer programming, one can get certifiably near optimal solutions, even at scale, to this very non-convex problem. And so by repeatedly solving the problem, you can actually construct a Pareto frontier of fairness trade-offs. So you can basically say like, what is the least I have to give in terms of predictive parity to get a higher demographic parity, for example, because you know that these conflict with each other at the most extreme case. And you also know that it's certifiably globally optimal. So you know this is the best possible trade-off you can get. And surprisingly, fairness trade-offs actually aren't that bad in practice. Like when we ran this experiment, I was expecting that like, oh, in order to get more of demographic parity, you have to give up like 5 or 10% in your original model's AUC. But it turns out that's not the case. You only have to give up like 1 or 2%, or sometimes even less than that. And it's very interesting because in real situations, these fairness interventions, you may think like, you know, 0.5 in AUC doesn't really matter much. But from a business perspective, it actually can matter a lot when you go and launch an A/B test for your model. So understanding these trade-offs, just from an intuitive standpoint, is very important for us practitioners. And even then, from an interpretability standpoint too, it's very nice to be able to like turn off or turn on or control the amount of fairness you have. And a lot of times that's done from an algorithmic standpoint by using regularizers. But that's not necessarily interpretable all the time. So it's something that like to think about essentially. Like, is it easy to understand what would have happened without your fairness, without your bias mitigation intervention? And that's why, like at LinkedIn, a lot of the mitigation solutions that we focus on post-processing. So, like from a maybe machine learning purist standpoint, we know that this isn't like the best thing you can do. But A, it's easy to operationalize because you can take any model and post-process the scores. It's interpretable because you can easily see what is before and what is after. And also, from an engineering standpoint, it's very difficult to go and understand all the models in your companies and develop a ad hoc mitigation solution that's in processing for them. So, there's a lot of really interesting and like really effective mitigation schemes out there that focus on changing the loss function or maybe doing some kind of warm starting or adding a regularizer. A lot of those, I'm sure they work great, and like I've seen them work in smaller scale data sets, but from an engineering standpoint, it's hard to append it to every type of model that we have. So that's basically the little side tangent that I wanted to go on, and the point that I wanted to convey. It's basically just awareness and adaptability in terms of how one can use these different fairness definitions. So that was the end of the interlude, and I'll go back to the principles now. So just as a refresher, in principle one, we talked about measuring and mitigating algorithmic bias. We had our four-step framework. We had this justifiability notion that if we want to use demographic or group information in mitigating our models, we have to justify it by exhausting that other methods don't work, methods that don't use this information at inference time. And so what do we do when algorithmic bias mitigation methods don't solve the entire picture, right? There are some cases where like no matter what you do, maybe your model performs equally well, or like maybe you've satisfied your fairness definition completely. And due to historical barriers, some people are still underrepresented. Well, there we want to focus on principle two, which is using algorithmic bias as more of a foundation for our equity strategy. So from this perspective, we want to essentially treat equitable outcomes by thinking about what kind of product interventions we can convey. And so this is really broad in that like it tries to go over our mission of creating economic opportunity, but as you can imagine, when it comes to product design, there's endless possibilities. So to give you a couple, just as a taste, one could be like we recently launched this thing called Self ID, which is LinkedIn's version of like the verification. Well, like Self ID isn't verification, but it's like one way of disclosing more information about yourself to LinkedIn. And so this would include things like allowing you to disclose your demographic attributes, your gender, etc. And so by doing this, we can improve our recruiter search strategy in the sense of like if you're a recruiter and you search for some results like software engineers and you see a bunch of males from a certain university and you're able to now we're able to give you suggestions of how you can change your search criteria in order to diversify your results better. So maybe we could say instead of searching for this university, you can exclude the university filter, or like instead of searching for this type of skill, you can look for an adjacent skill that has broader diversity. So these are the kinds of things that we want to think about. Basically, like, okay, if the candidate retrieval process, which is an AI model, works perfectly well from an algorithmic standpoint, but the candidate pool is small, what can we do about that from a product perspective? That's one example. Another is like explore and exploit. So this is addressing the common notion that there's label bias or position bias in a lot of these ranking models. So in order to prevent these rich get richer type of effects that we see in things like you can imagine recruiter search or people you may know, where popular users get shown because, in some sense, because they're popular. One thing we can do is basically go with explore and exploit. So sometimes collecting randomized data and updating our AI models to make sure that it doesn't follow through. And you'll see that in some cases, these two are like compatible with what we want from algorithmic fairness too. So that's nice. Another example actually that's not here is skills-based nudges. So like if you've noticed, LinkedIn has a lot of these skills that you can add onto your profile. And sometimes when recruiters use like a recruiter search or like when advertisers are posting jobs, they tag a bunch of skills that they want to see out of their candidates. And if we don't see that skill, then like we want to explore a product where we can nudge you to include something that you may have, so that recruiters or job posters can get a better signal of who you are and what background you come from. So yeah, these kinds of product-based nudges or like product-based strategies are basically to address things that algorithmic bias cannot. And we see this as like we see them as two sides of the same coin of how to achieve equity at the end of the day. Okay, so the last principle here is basically communicating this information externally. So we want to give a lot of talks like these. We have an engineering blog where we hope to publish more about what we're doing exactly and give the world a broader perspective of what we're doing with algorithmic fairness, how we think about it, some specific case studies where we've actually applied it. And we want to leverage the input that we have. So we work with people outside of LinkedIn. We have LinkedIn Scholars as a program where we work with professors and universities and discuss some of these problems. Yeah, this is basically another pillar in our equity strategy of trying to be transparent and trying to be specific with these case studies in order to receive feedback. So we're more than happy to learn about approaches that you've taken or what you think of what we're doing. Okay, so those are the three principles, and now I want to go into a case study of how we actually applied these things. So the case study, which was done about a year ago, is on a product called People Also Viewed. And People Also Viewed is basically on the side tab. If you go visit someone's profile, they have suggestions about like who else has viewed a certain profile. So these are some LinkedIn candidates that like you would see that usually are similar to whoever you're currently viewing. And it's a major source of profile traffic for LinkedIn. And so the case study is going to cover how we measured predictive parity fairness and mitigated it under a justifiability framework, as well as measured the outcomes afterwards. So getting into it, um, the model that produces these rankings is a point-wise scoring model. So for each candidate, it'll produce a certain score and we'll rank them based on that score. And the fairness measurement that we'll be using is so-called predictive parity. And so what this measures is essentially, is your expected outcome conditioned on score equal to equal across the groups? So this would be a problem basically if two people get the same score or very similar scores, but one person's expected outcome is a lot higher, right? In words, that basically means I give you the same score and the same opportunities, but one person's qualifications are actually a lot higher. And so by giving them the same score as someone with lower qualifications, I'm being biased against them. And we measure that through a plot like this. So if you see a gap between the two lines, that essentially means there's a gap in the predictive parity measurement. So one way to fix this is essentially by calibrating the model. You can see that, but if I calibrate the model, then I'm basically pushing both of these two lines onto the diagonal where your score corresponds to your expected outcome exactly. And through that, that's one way to close the gap between these two calibration plots, essentially, right? And so why would this happen? First of all, this is like a part of our root cause analysis. It could be lack of data. It could be that some features only benefit one group and don't benefit another. It could be Y given X distribution shifts in the data. I'll talk a little bit about what that means later. There could be a lot of reasons. And so we did a bunch of basic checks to see what could be the drivers of this. And again, we know that when it comes to mitigation, adding gender into the model will automatically fix the issue. In fact, like all we did was just include gender into this model and the lines instantly overlap. So like this is, I guess, a practical case of some of the recent theoretical works where including gender or like having features that convey information about gender is actually like good for algorithmic fairness. But again, just because we know that that's a solution doesn't mean we can jump to it or it should be our first solution. So, following this whole justifiability framework approach, what we did was try a bunch of strategies, these alternative mitigation strategies, to see how well they can do. So, you'll see some in this graph, things like you'll see adding gender completely close the gap. But some of these other things like imputing missing values, we tried sampling. We tried some custom algorithms like this causal effect decomposition. We tested a bunch of things basically to see which ones could help. And none of them were really able to close the gap as much as we would like. And More recently, I've been exploring these different in-processing algorithms as well. So things like distributionally robust optimization, if anyone's seen that, is actually an approach that we're heavily investigating. Um, After determining that these approaches didn't work so well in closing predictive parity, we sought our post-processing model solution, which uses the group information at inference time to basically calibrate the model. It's a little more sophisticated than like what I'm about to say, but essentially think of it as just like a group-based calibration. So we build a calibration model for each group, and then we post-process the scores afterwards. And so in an offline test, we were able to basically make these two lines close together. And in an online test, we were able to, basically, as you can see, close these gaps between each other. Most significantly, which we thought was very interesting, was that like we saw an improvement in the product metrics. So this both improved the model and improved the fairness. And for certain fairness definitions, this is actually something you'd expect. So in this case, predictive parity, it's a statement about essentially how well calibrated your models are, right? And so you would expect that if your models are really well calibrated, the outputs are also good relative to each other. So this was a case where model algorithmic fairness can actually improve the business outcomes. Next, what we did was measure the unintended consequences. So this was what I was mentioning earlier of like, okay, if we know that we're improving the scores for females or like we're boosting the scores for females on average, then does that result in anything that's unwanted? Like, do they get unwanted messages? Are they reporting people more? These are actually metrics that we checked. It was essentially for people that saw the intervention, that for people whose um, people also view tab was produced by the intervene model. Are they causing essentially bad reactions? Like when they click on profiles, is the destination side ignoring them more frequently? Are they reporting them more frequently? So this is now a test that we check whenever we launch a mitigated model. And so to summarize this case study, the first thing we did was measure and mitigate our AI models. The next thing was we launched an experiment and we concluded by doing this unintended consequences analysis to make sure that things align with product and legal objectives. And so to summarize everything I've discussed so far, we set forth our three principles, right? One is we will measure and mitigate our AI models with the perspective of equal treatment. Two is we don't see equal treatment as the end all be all. We want to complement the strategy in our responsible AI work with product initiatives in order to deal with historical barriers and measure unintended consequences. And three is we'll continue discussing these strategies with external stakeholders and leaders in the field. And our case study gave us an example of how we exactly operationalize some these things that we just discussed. Okay, so that's it for like the main talk. I also want to just give a brief note on the current research that we're doing in our team. So one is this growing body of distribution shift work, and this is very ripe for understanding fairness and mitigation. Interestingly, a lot of the distribution shift work I think started from an observation that like these large ML models can fit on spurious correlations. The distribution shift work is largely about like, okay, if you go from training to testing set, was there something that changed within your data that causes your model to degrade in performance when you go from training to your production data set? And how can you understand why that disparity exists? Is it because of a shift in a certain feature? Is it because the labels given the same feature are now different? Right. So But if you think about that exact kind of sentiment is very ripe for analyzing it from a fairness perspective too, right? Because essentially we want to know why is the model performing bad, good for one group and bad for another? Is it because when we go from males to females, females don't have a certain type of feature? Maybe in a different world, like females join LinkedIn later than males and therefore just have fewer historical features or like fewer characteristics. Or is it possible that we don't observe all the features that we need? And so like from our perspective, even conditioning on the same exact set of covariates, males and females have different preferences. Um, can we use this distribution shift literature to diagnose and explain why we're observing the model performing well on one group and poorly on another? So this is in my opinion, like a really interesting line of work. Yeah, it's something that I think has a lot of applications outside of the origination, which is analyzing spurious correlations. Um, and the second topic is, can we avoid this rich get richer problem in online recommendation systems through uncertainty quantification? So I talked previously about one of the product strategies, which was essentially applying randomization before in order to collect our model to prevent these kinds of things. But in some sense, randomization is like an easy way out. Like even if you randomize, it doesn't mean you're necessarily capturing the people that are unrepresented. What you want to do ideally is explicitly target that population. So you want to say like on what segment is our model currently very uncertain of, and because they're uncertain, is the low score that they're getting justified? So if there's a way to do this uncertainty quantification at scale across different kinds of models and across different applications, then this is potentially one way to really capture that and like be targeted when we do this randomization to improve outcomes for unseen groups. And then the last topic here is how does fairness in models actually impact downstream outcomes? So I talk a lot about like how algorithmic fairness and like things confined in this space of like you have X and Y and you want to have some fairness with respect to this label Y. But in real life, in like our business, a lot of times the Y is just a proxy for some downstream metric that we actually want to optimize for. And I think this is true for essentially like all tech companies. You can't directly observe maybe like your sessions, which is a common metric that social media cares about. So what you do is you optimize for a proxy of that. You say like, oh, maybe the number of times you visited or like how much your engagement is each time you visit. And so you have a set of proxies for what you actually measure as the downstream utility for the user. And so these kinds of things are currently not discussed as much, and I think for good reason. It's because like it's a very difficult situation, right? Like you have your label and you have whatever your label is supposed to be a proxy for. But what does fairness mean in that context? Like, is there any notion of qualification left, or is it more so just we have to go for demographic parity? And so these are ideas that like our team is currently thinking about researching. And that's basically all I've got. So these are some papers that like our team has presented recently. You'll see a lot of them are in FACT, which is a fairness conference. But if you have any interest in them, or if you want to discuss them, if you have any feedback for our team, like our principal thing, we're happy to discuss them. And I'm really interested in seeing what the academic world or other practitioners think about our approach as well. So that's all. And thank you all so much for your attention. I'll stop for questions.